All right. Hi, everyone, and welcome back. In the next set of video, I will try to discuss how the Riemann tensor can help us to describe space-time curvature. But first, I would like to try to understand why space-time should be curved at all. Why do we speak about curvature of space-time, or more precisely, why gravity should be interpreted as a curvature of space-time? Why should massive objects bend the fabric of space-time? Why is that? So that's the topic of the day. Let me share a whiteboard, and also before the video starts, no, that's not that. Before the video starts, please feel free to adjust the playback speed. I think that 1.25 would be good for more fluidity. Okay, yeah, a whiteboard. Okay. So why should space-time be curved? And by be curved, I mean be curved uh, by massive objects. Yes. So to understand that, we first have to consider flat space-time. So let's consider flat space-time, and let's not talk about gravity yet. So no gravity, flat space-time, no gravity. And this is what we usually call special relativity. Okay, flat space-time. So if I draw a space-time diagram, with the trajectory through space and time of any object or anyone, that would look like something like this. So this is what we call a word line. So that's the word line of, let's say, maybe someone that would be called Paul. And we can say that Paul would be somewhere here on this word line for Christmas, and here for summer vacation in July. But that's the word line of Paul. That's basically the trajectory that describes the life of Paul through space and time. On his word line, we can graduate his word line with the proper time of Paul. Because through space-time, you will never experience your clock ticking faster or slower. A second will always be a second for you. So your proper time is the perfect tool to graduate your word line. So I can graduate it from -3, -1, 0, 1, 2, 3. It's just the seconds that are passing by on Paul clock. It's his proper time. And one interval will be called delta tau. Tau is for proper time. So delta tau is an interval of proper time. Paul's proper time. Okay. Now what we need to measure distance is the line element of this flat spacetime. So a line element, if I draw something here, a line element usually in the XY plane. So here let's forget about time just a second. And here is just a plane in space, so the XY plane. Any curve can be described by its line element, ds. So it's an infinitesimal step on the line. So let's say that the line should be much bigger and ds will be like this. It's an infinitesimal step on this trajectory, but if I zoom, and I can draw it like this. And so we see that this is an infinitesimal step in the x direction, and this is an infinitesimal step in the y direction. And by Pythagoras, I know that the s squared, because that's a square triangle, will be equal to the x squared plus the y squared. And that's we commonly call a line element. So that would be the line element for the xy plane that could describe any curve on the xy plane. But now we need a line element for our flat spacetime. And this is given by what we call a Minkowski line element. The s squared equal minus tt squared plus dx squared plus dy squared plus dz squared, the three direction in space. Okay, and so this line element in my space-time diagram will help me to measure space-time distances. So this ds squared will help me to measure space-time distances. But we already introduced proper time as a graduation of the world line of any object in space-time. And there is a relation between proper time d tau square and proper and distance that you would measure in space-time. It's this one. And this relation is very important because it will give you the proper time of anyone according to this proper time of anyone according to the space-time distance that you measure. That's a space-time curve in a space-time diagram, and you can measure space-time distance on it, just as we did here in 2D space, but now we are in 3+1 space-time. 3 dimension of time of space and 1 dimension of time. Now there is something that I don't understand yet very well why it's here, but if you notice, we have a minus here and here, and this should tell you that time and space, even though we need both to describe someone in space-time, time and space are intrinsically very different. That is, in time, you can only go in one direction, which is from past to future. And actually, it's not even a direction when you have any freedom. It's just the flow of time. Nobody can stop it. A second on your clock will always stay a second. But in space, it is well known that you can go up and down, you can go left and right, and you can go back and forth. Yes, so if you want to go back on your step, you can, but if you want to go back in the past, you cannot. You cannot stop the flow of time. And this is how a minus end up here. It tells us that intrinsically time and space are very different by nature. Okay, but time, dτ and ds are two ways to measure space-time distances. So we have this relation that I have unboxed in red. Sorry, just a second. My pen is not drawing anything. Yeah, my pen is not. Okay, it came back. Sorry. Okay, so with that said, now let's see what does. Yeah, let's just go on. So dτ square equal minus ds square, or I can also write ds square equal minus. No, I just wrote the same thing. Sorry. Dτ square equal minus ds square. So dτ equal square root of minus ds square. But now this line element ds square is given by the Minkowski line element that you have here. And so I can write that it's equal to dt square minus dx square and minus dy square minus dz square. But I can just consider one direction in space for the compression of. So dτ equal square root of dt square minus dx square, and this I can factorize by dt squared 1 minus dx square of dτ square. This dx can represent the three space direction if I add the I. So for example, x1 will be x, x2 will be y, and x3 will be z. So I just call it xi now. No, sorry. Yes, so I can factorize by dt square under the square root as is. And this, sorry, and here it's dt square. T. Yeah, and this is just our velocity squared. This is just our velocity squared. And this dt squared, I can take it out of the square root now if I want. So let me rewrite this as square root of 1 minus v squared dt. All right. So now we have derived another very important relation, which is that dτ equal square root of 1 minus v squared dt. Okay. And in this relation, I have not said from the beginning, but we assume that the speed, the light speed, the celerity c equal 1. And so by definition, it's infinity, it's not reachable. So v can only be smaller than 1. And of course, bigger than 0. There is, yeah, so we say that v equal 1 is infinity. So v will be equal something between 0 included and 1 excluded. Okay. Yeah. Okay, so what does it tell us here? It tells us that if it tells us that the quicker the velocity of an object is measured by an observer with time t, the slower your proper time will seem to pass. We see here that uh, the bigger will be v and the smaller will be tau. So if v equals 0, if an observer measure someone with non-velocity, then his proper time is equal to the time of the person that is measuring. But if v is different than 0, then we see that d tau will be inferior than dt. Because square root of 1 minus, let's say, maybe something 0.2 t equal to tau. This is less than 1 time dt. So d tau will be smaller than dt for any non-null velocity. Okay, but maybe I should take an example. All right, I believe that you will understand that much better with an example. So, all right, let's say you are on Earth. So this is you on Earth, and you're looking at a rocket only going in the x direction from point A to point B. You have your time, that is the time that you use for to do measuring, I mean to measure stuff. So this is the time that we call t, and this is supposed to be a clock. And inside the ship, there is also a clock that we call tau, the proper time of the ship, of the rocket. All right. If you measure that the rocket from point A to point B took 20 seconds, so you measure 20 seconds, the person in the rocket looking at the proper time of the rocket will probably measure something like 19.9 seconds if you go at relativistic speed. So I can say that v here is, yeah, something like maybe 0.8 of the light speed. So it's a relativistic speed. It means it goes very fast. You will measure different time. So yes, so if you can look at the clock in the spaceship, it will, for you, it will seems like the clock in the spaceship is slower because in 20 seconds, it only took 19.9 seconds. And if the person in the rocket look at your clock, it will seems like your clock is running quicker because in 19.9 seconds, your clock will display 20 seconds. So now we see that time is relative. All from this derivation here. All right. All right, so I think I will do, I did half of what I wanted to say about why spacetime should be curved. I'm gonna just take a small break and everything will be in the following video. So this was sort of an introduction to the math that we need from special relativity to understand how relativistic speed can influence time. And in the next video, we're gonna see why gravity field should be interpreted as a curvature of the fabric of space-time. Okay, so see you in the next video.